Hello and welcome. Tonight we are going to drift toward Mars. Not the Mars of old science fiction, not a world of canals, ancient cities, or green skies, but the real Mars. Cold, dry, dusty, distant. A planet with frozen deserts, thin air, ancient riverbeds, polar ice, giant volcanoes, deep canyons, and a sky that has waited silently for billions of years. For centuries, Mars has lived in the human imagination. It has been a red point of light in the night sky, a symbol of mystery, war, exploration, and possibility. But today, Mars is no longer only a dream seen through telescopes. It is becoming a destination with plans, rockets, architecture, landers, power systems, habitats, rovers, and engineering problems that must be solved one by one. The question is no longer only, can humans go to Mars? The deeper question is, how? How do you carry people across millions of kilometers of space? How do you land heavy cargo on a planet with an atmosphere too thin to slow you easily, but thick enough to create dangerous heating? How do astronauts survive radiation, dust storms, freezing nights, low pressure, and months of isolation? How do they breathe? How do they drink? How do they grow food? How do they return? And if the first missions succeed, how does a temporary expedition slowly become a permanent human presence? Tonight we will follow the road to Mars as it is being imagined by NASA and SpaceX. NASA's path is careful, layered, and built around a larger Moon-to-Mars strategy. It begins close to home, with Artemis missions to the Moon, where astronauts can test deep space systems, surface habitats, rovers, power, spacesuits, landing technologies, and life support before attempting the far longer journey to Mars. SpaceX's vision is more direct and more ambitious in scale. It centers on Starship, a very large reusable spacecraft designed to carry cargo and eventually people to the Moon, Mars, and beyond. In SpaceX's vision, Starship is not only a rocket. It is the foundation of a transportation system: launch, refuel in orbit, travel to Mars, land heavy cargo, make propellant from Martian resources, and build toward a self-sustaining settlement. These are not the same plan. NASA and SpaceX are connected, but they are not identical. NASA is a government space agency with scientific, safety, international, and political responsibilities. SpaceX is a private company building transportation systems at high speed with its own long-term goal of making life multiplanetary. Their paths overlap. NASA uses commercial partners, including SpaceX, for parts of Artemis and human landing systems. SpaceX depends on Starship, which NASA is also relying on for lunar missions. The Moon becomes a proving ground. Starship becomes a possible bridge. Mars becomes the distant destination. But this story must be told honestly. There is no finished road to Mars yet. There are plans. There are prototypes. There are test flights. There are architecture documents. There are engineering studies. There are dreams. There are major unsolved problems. And between Earth and Mars, there is still an enormous distance. So settle in. Let the room grow quiet. Let the red planet rise slowly in the dark. And imagine not just a single rocket leaving Earth, but an entire chain of machines, people, missions, habitats, vehicles, power systems, and choices slowly forming a path across space. The first part of the journey begins on Earth. Every Mars plan starts with one basic truth: Earth is a deep gravity well. To go anywhere in space, a spacecraft must first climb away from our planet. Rockets must fight gravity, atmosphere, drag, heating, vibration, and enormous mechanical stress. They must carry fuel, structure, engines, cargo, and sometimes crew, all while accelerating to orbital velocity. Getting to orbit is already difficult. Getting from orbit to Mars is another challenge. And landing on Mars is another challenge after that. This is why reusable rockets matter. For most of space history, rockets were used once. A rocket would launch, do its job, and large parts of it would fall away into the ocean or burn up in the atmosphere. This made spaceflight incredibly expensive. It was like building an airplane, flying it once and throwing it away after every trip. SpaceX changed part of that equation with reusable Falcon boosters, showing that large rocket stages could return, land, and fly again. Starship is meant to take that idea much further. The goal is full reusability. The Super Heavy booster returning after launch, the Starship spacecraft returning after orbit or deep space missions, and the entire system flying again and again. If full reusability works at large scale, the cost of placing mass into orbit could fall dramatically, and Mars needs mass. A human Mars program is not one tiny spacecraft. It is tons and tons of food, water, oxygen, fuel, tools, spare parts, habitats, rovers, power systems, science equipment, medical supplies, communications hardware, landing pads, construction materials, and emergency reserves. Mars is not a camping trip. It is a logistics problem on another planet. NASA approaches this through architecture. In ordinary life, architecture means buildings. But in NASA's Moon to Mars language, architecture means the system of systems needed for exploration. It is the chain of capabilities, launch vehicles, crew vehicles, habitats, landers, spacesuits, power, communications, mobility, science, cargo, life support, and return pathways. NASA does not see Mars as one isolated mission. It sees it as part of a sequence. First, Earth orbit, then the Moon, then longer stays on and around the Moon, then systems that can support humans farther away, then Mars. The Moon matters because it is close compared with Mars. The Moon is about 3 days away by spacecraft. Mars is months away. If something goes wrong on the Moon, help is still difficult, but Earth is near. Communication delay is only a little over 1 second each way. Supplies can be sent more often. Missions can test hardware in a harsh environment without being completely cut off. Mars is different. Depending on where Earth and Mars are in their orbits, the distance between them changes enormously. A mission to Mars usually takes advantage of launch windows that open roughly every 26 months when the planets are positioned favorably. The journey can take many months. Communication delay can range from several minutes to more than 20 minutes one way. A real-time conversation is impossible. If astronauts are on Mars and something breaks, Earth cannot talk them through it instantly. If they need a replacement part, it cannot arrive tomorrow. If they need to leave, they cannot simply launch whenever they want. Mars demands independence. That is why NASA wants to learn on the Moon first. The Artemis program is the near-term foundation of this journey. Artemis is designed to return humans to the Moon and develop more sustained exploration than Apollo. Apollo was extraordinary, but it was brief. Astronauts landed, explored for short periods, collected samples, deployed instruments, and returned. Artemis is meant to build longer duration capability, repeated missions, surface mobility, lunar habitats, power systems, and operations near the lunar South Pole. The South Pole of the Moon is important because some permanently shadowed regions may contain water ice. Water is one of the most valuable resources in space. It can support life. It can be split into hydrogen and oxygen. Oxygen can be used for breathing. Hydrogen and oxygen can be used as rocket propellant. Even if extracting lunar water proves difficult, learning how to find, mine, process, store, and use resources on another world is directly relevant to Mars. Mars also has resources. It has carbon dioxide in its atmosphere. It has water ice in the ground and at the poles. It has regolith that could be used for construction or shielding. But using these resources is not simple. You need machines that can operate in dust, cold, low pressure, and reduced gravity. You need power. You need reliability. You need storage tanks. you need chemical processing, you need maintenance, you need backup systems. This is called in situ resource utilization, using what is already there. For Mars, one of the most important ideas is making propellant on the surface. SpaceX's Mars plan depends heavily on this. Starship is designed to use methane and oxygen as propellant. Mars has carbon dioxide in its atmosphere and likely water ice in accessible regions. With water, carbon dioxide, and enough energy, it is possible in principle to produce methane and oxygen using chemical processes such as electrolysis and the Sabatier reaction. The basic idea is this: use electricity to split water into hydrogen and oxygen. Combine hydrogen with carbon dioxide from the Martian atmosphere. Produce methane and water. Recycle the water. Store the methane and oxygen as rocket propellant. If this works at large scale, a Starship could land on Mars with cargo or crew, then refuel using Martian resources and return to Earth. Without this, returning from Mars becomes much harder because the return propellant would have to be brought from Earth. That is heavy. Very heavy. Carrying fuel to Mars so that you can leave Mars means launching far more mass from Earth. Making fuel on Mars is one of the key ideas that turns Mars from a one-way dream into a practical round-trip architecture. But it has not yet been demonstrated at the necessary scale. NASA's Perseverance rover carried a small experiment called MOXIE, which produced oxygen from Martian carbon dioxide. It was a technology demonstration, not a full industrial plant. It showed that oxygen production from the Martian atmosphere is possible on a small scale. But producing enough oxygen for a crew, or enough oxygen and methane for a large spacecraft, would require a much larger system. A Mars base would need power first. Power is everything. Without power, there is no oxygen production, no water extraction, no communications, no heating, no lighting, no computers, no science instruments, no greenhouses, no fuel production, no life support. Mars receives less sunlight than Earth because it is farther from the sun. Solar power can work on Mars, but dust is a problem. Dust can settle on panels, reducing output. Dust storms can dim sunlight across wide regions. Nights are cold, winter is colder. Equipment must survive and keep working. NASA has studied nuclear power for Mars because it can provide steady electricity regardless of sunlight or dust storms. Small fission power systems could support habitats, science operations, and resource processing. Solar arrays may also play a role, especially if they can be cleaned, deployed in large numbers, and paired with energy storage. A real Mars outpost may use both: solar power spread across the surface, nuclear power for steady baseline energy, batteries, fuel cells, or other storage for night and emergencies, cables or local grids connecting habitats, rovers, production plants, landing zones, and communications towers. This is where the dream becomes infrastructure. The first missions may look heroic, but the long-term plan looks more like construction. Landing pads, power cables, habitats, storage tanks, water processing units, radiation shelters, weather stations, communications antennas, rovers, spare parts, workshops, robotic assistants, navigation beacons, science labs, medical areas, greenhouses or food growth experiments. Mars is not only a destination, it is a place where every kilogram matters. This is why cargo missions may come before crew. In most serious Mars architectures, you do not send humans first into an empty desert and hope everything works. You send cargo ahead. You land supplies before the crew leaves Earth. You confirm that critical systems survive landing. You test power. You test communications. You begin producing oxygen or propellant. You make sure the return system is ready. Only then do astronauts depart. A careful Mars mission may require proof that the crew can come home before they ever leave Earth. This is especially important because of the timing of Mars launch windows. A crew might stay on Mars for many months, perhaps more than a year, depending on the mission design. Fast missions are possible in theory, but they require more energy. Longer conjunction. Class missions use planetary alignment more efficiently, but they mean the crew lives far from Earth for a long time. This is not like Apollo. Apollo astronauts spend days in deep space. Mars crews may spend years away from Earth. The spacecraft itself must become a home. During the transit to Mars, astronauts need radiation protection, life support, exercise systems, food, water recycling, waste management, medical equipment, privacy, sleep quarters, workstations, and psychological stability. They must live in a closed environment, far from Earth with no quick rescue. Radiation is one of the biggest problems. Earth's magnetic field and atmosphere protect life from much of the radiation in space. Astronauts traveling to Mars would be exposed to galactic cosmic rays and solar particle events. Galactic cosmic rays are high-energy particles from outside the solar system. Solar particle events can come from eruptions on the Sun and deliver dangerous doses over short periods. Spacecraft need shielding, but shielding adds mass. Water, fuel, food, equipment, and specialized materials can help. Some designs place supplies around crew areas to provide protection. A storm shelter might be built into the spacecraft, a small area with extra shielding where astronauts can take refuge during solar events. On Mars, the atmosphere is thin and the planet has no global magnetic field like Earth's. Radiation on the surface is higher than on Earth. A Mars habitat may need to be covered with regolith, built partly underground or protected with water, equipment, or other shielding. This is why the first habitats may not look like shiny domes. Glass domes are beautiful in art, but not very practical at first. A real Mars base may look low, covered, modular, and partly buried. It may use inflatable habitats inside protective shells. It may use hard pressure vessels delivered from Earth. It may use buried modules. It may use tunnels or lava tubes someday, if safe and accessible ones are found. It may use local soil piled over living spaces to reduce radiation exposure. The romantic Mars city may come much later. The first base will likely be more like an Antarctic research station crossed with a spacecraft and a mining site. Pressurized, dusty, mechanical, carefully monitored, every system redundant, every leak serious, every repair important. Mars dust is another challenge. It is fine, dry, and widespread. It can cling to surfaces. It can wear down seals and joints. It may be chemically irritating or toxic in some forms. Astronauts would need ways to keep dust out of habitats. Airlocks, suit ports, cleaning systems, and careful procedures would all matter. Spacesuits must handle dust, low pressure, cold, mobility, gloves, communications, oxygen, cooling, and safety. NASA is working on next-generation spacesuits for lunar missions, and lessons from the Moon will matter for Mars. The Moon has a brace of dust and vacuum. Mars has dust too, but also a thin carbon dioxide atmosphere, wind, and different thermal conditions. Mars suits must support longer surface operations and perhaps more frequent work outside. Mobility matters because Mars is large. The Moon is smaller and closer, but Mars has entire landscapes waiting, ancient river valleys, lake beds, deltas, volcanic plains, polar layers, canyon systems, impact craters, and minerals shaped by water. Human explorers could travel farther and work faster than robotic rovers, but only if they have vehicles. Pressurized rovers could let astronauts drive long distances without wearing suits the entire time. Unpressurized rovers could support shorter excursions. Drones may scout terrain. Robots may move cargo, inspect equipment, prepare landing zones, or explore dangerous areas before humans arrive. Communication infrastructure will also be needed. Mars missions today rely on orbiters as relay satellites. Future crewed missions would need strong communication links between surface habitats, rovers, astronauts, orbiters, and Earth. Because of the time delay, astronauts cannot rely on mission control for every decision. They will need autonomy, planning tools, onboard expertise, and perhaps artificial intelligence support. A Mars base will need local networks, radios, satellites, surface antennas, navigation systems, emergency beacons, data storage. Scientific instruments will produce huge amounts of information. Crew health systems will send data. Rovers and robots will need coordination. Weather monitoring will matter. Dust storms must be tracked. Power systems must be managed. The road to Mars is not only a rocket road. It is an information road, a power road, a supply road, a maintenance road. This is why NASA's Moon to Mars approach is so broad. It is not simply about planting a flag. It is about building the capabilities that let humans live and work in deep space. Artemis tests pieces of that future. Orion tests crew transport beyond low Earth orbit. The Space Launch System provides heavy lift for NASA crew missions. The Gateway, planned as a small station near the Moon, is meant to support lunar operations and deep space experience. Human landing systems bring astronauts to the lunar surface. Surface habitats test living away from Earth. Rovers test mobility. Power systems test long-duration operations. Cargo landers deliver equipment. Spacesuits let astronauts work outside. Robotic missions scout resources. Each piece teaches something. Some lessons will transfer to Mars, some will not. The Moon and Mars are different worlds. The Moon has no atmosphere. Mars has a thin one. The Moon is 3 days away. Mars is months away. Lunar gravity is about 1/6 of Earth's. Martian gravity is about 38% of Earth's. The Moon's day-night cycle is about a month long. Mars has a day only slightly longer than Earth's, but the Moon is still the best nearby testing ground. It teaches surface operations. Dust management, power storage, habitat design, remote logistics, crew autonomy, partial gravity living, landing near difficult terrain, using local resources, working in spacesuits for long periods. NASA's view is that Mars is not reached by one leap, but by building experience step by step. SpaceX's view is that Mars becomes possible when transportation becomes large, reusable, and frequent. Starship is central to this. In SpaceX's Mars architecture, a Starship launches from Earth on top of a super-heavy booster. The booster returns to be reused. Starship reaches orbit, but to go to Mars with significant payload, Starship must be refueled in Earth orbit. That means launching tanker Starships, transferring propellant in space, filling the Mars-bound Starship, and then sending it on its interplanetary trajectory. Orbital refueling is one of the key technologies. Without it, Starship's deep space capability is limited. With it, a large reusable spacecraft could leave low Earth orbit carrying far more mass to the Moon or Mars. But orbital propellant transfer at this scale is difficult. Cryogenic propellants must be managed in microgravity. Boil-off must be controlled. Docking must be reliable. Multiple launches must be coordinated. Tankers must operate efficiently. The system must work not once, but repeatedly. For Mars, many launches may be needed for one fully fueled departure. This is why Starship is not just a vehicle. It is an operations model, frequent launches, rapid reuse, propellant transfer, cargo versions, crew versions, tankers, depots perhaps, Mars landing variants, surface systems, return vehicles. Everything depends on the system becoming routine enough that Mars cargo can be sent in large amounts. SpaceX's long-term vision goes far beyond a scientific outpost. The company speaks of a self-sustaining city on Mars, requiring enormous numbers of people and huge amounts of cargo over time. This is not a near-term NASA mission plan. It is a long-range settlement vision, far beyond what has been demonstrated. A self-sustaining city would require not only rockets and habitats, but industry, food production, water extraction, fuel plants, construction, metalworking, chemical manufacturing, medicine, electronics repair, spare parts, radiation protection, governance, emergency systems, education, waste recycling, agriculture, mining, manufacturing. A city is not built by landing a few rockets. A city requires supply chains. On Earth, every city is supported by the entire planet. Farms, mines, factories, oceans, roads, power plants, hospitals, trade networks, and millions of people doing specialized work. A Mars city would need to recreate a small part of that independence in one of the most hostile environments humans have ever tried to enter. That is why self-sustaining is such a hard phrase. A Mars base could exist with constant resupply from Earth. A Mars settlement could grow with regular cargo ships, but a truly self-sustaining Mars city would need to survive even if Earth stopped sending support. That is an enormous challenge, maybe possible in the very long term. Not proven, not close. But it is the direction SpaceX uses to think about scale. NASA's more immediate goal is different: human exploration, science, technology demonstration, and eventually sustained presence. These goals can work together in some ways. NASA needs transportation and landers. SpaceX needs large-scale missions and customers. Both need better life support, better landing systems, better power, and better surface operations. Both benefit from learning how to use local resources. Both must solve Mars entry, descent, and landing. Landing on Mars is famously difficult. The atmosphere is thick enough to create heat during entry, but too thin to slow heavy spacecraft with parachutes alone. Small robotic landers can use heat shields, parachutes, retro-rockets, airbags, sky cranes, or combinations of these. But human missions need to land much heavier payloads. Habitats, power systems, ascent vehicles, rovers, cargo ships, human-rated spacecraft. A Mars base may require landing tens of tons at a time, perhaps more. That is far beyond the mass of most successful Mars landers. Starship's concept is to enter Mars's atmosphere using its heat shield and body shape, slow down through atmospheric drag, then use engines to land propulsively. This is bold. It could land very large payloads if it works. But Mars entry and landing at Starship scale must be proven. NASA has also studied heavy Mars landers for many years. Inflatable heat shields, supersonic retropropulsion, precision landing, and advanced guidance systems may all play roles. The key challenge is landing large mass safely and accurately near a chosen site. Accuracy matters because infrastructure must be close together. You cannot land a habitat 100 kilometers away from the power plant. You cannot land the return vehicle beyond walking distance. You cannot scatter supplies randomly across Mars. A real base requires precision. Cargo must land near cargo. Crew must land near their habitat. Fuel plants must be near water resources. Power systems must connect to equipment. Rovers must reach everything. Landing zones may need to be prepared. Rocket exhaust can blast dust and rocks at high speed. On the Moon, this is a major concern because there is no atmosphere to slow particles. On Mars, the atmosphere changes the behavior, but dust and debris remain a problem. Repeated landings near a base could damage equipment unless landing pads, berms, or safe distances are used. This means early missions might include construction robots or surface preparation tools. Before a large human base grows, Mars may need a port, not a harbor with water, a landing zone. A flat, mapped, stable region where spacecraft can arrive repeatedly. Nearby, there must be access to water ice if propellant production is planned. The site must have decent sunlight if solar power is used. It must be scientifically interesting. It must be safe to land. It must not be too cold, too dusty, too rocky, too high in elevation, or too far from resources. Site selection is one of the most important choices. Mars is not equally useful everywhere. Low elevations help landing because there is more atmosphere above the site to slow the spacecraft. Mid-latitudes may offer access to buried ice. Equatorial regions get more sunlight. Polar regions have ice but are colder and have extreme seasonal issues. Ancient lake beds are scientifically rich but may not be ideal for early industry. The first human Mars base will likely be a compromise. Safe landing, resource access, power potential, science value, communication, terrain, temperature, dust, everything matters. Once cargo arrives, robots may begin work before humans. They may deploy solar arrays, check systems, set up antennas, test oxygen production, scout the area, move supplies, inspect landers, monitor weather, perhaps begin extracting water. If fuel production is part of the mission, it may need to begin long before the crew arrives. Producing enough methane and oxygen for return could take months or longer, depending on power and system size. Storage tanks must keep propellant cold. Equipment must survive dust, thermal cycling, and mechanical wear. Only when enough return propellant exists, or when another safe return method is ready, would a crewed mission be considered. Then astronauts launch. They leave Earth, perhaps in a Starship, perhaps in another deep space transport, depending on the architecture. They spend months traveling through interplanetary space. They see Earth shrink into a bright point. They live inside their spacecraft following schedules, exercising to reduce bone and muscle loss, maintaining systems, conducting science, monitoring radiation, and preparing for arrival. Mars grows slowly ahead, a red disk. Then a world, clouds, dust, polar caps, dark volcanic plains, canyons, craters. The spacecraft approaches at high speed. Entry begins. The heat shield glows. Plasma forms around the vehicle. Communications may be interrupted. The atmosphere screams past. Guidance systems adjust the path. The vehicle slows. Engines ignite. Dust rises. And for the first time, humans land on Mars. That moment will be one of the great moments in exploration history. But the landing is not the end. It is the beginning of the hard part. The crew must survive the first hour, then the first day, then the first night, then the first dust storm, then the first equipment failure, then the first long-distance rover trip, then the first return launch. Mars will not care that humans have arrived. It will remain Mars, cold, dry, quiet. Its atmosphere is mostly carbon dioxide and less than 1% of Earth's surface pressure. A human exposed without a suit would not survive. Liquid water is unstable on the surface under most conditions. The sky can turn dusty. Temperatures can fall far below freezing. Radiation continues. The ground is alien. The horizon is familiar and not familiar at the same time. Everything outside the habitat is hostile. Everything inside must work. The first habitat may already be waiting, delivered by cargo mission. It may be a pressurized module, an inflatable structure, a modified lander, or a cluster of connected units. It must provide air pressure, oxygen, carbon dioxide removal, humidity control, temperature regulation, fire detection, water recycling, waste management, sleeping areas, workstations, food preparation, medical care, and emergency shelter. Life support is not optional. On Earth, life support is the planet. On Mars, life support is machinery. Machines become the atmosphere. Machines become the water cycle. Machines become the difference between survival and death. This is why closed-loop systems matter. The more water and oxygen a crew can recycle, the less must be brought from Earth. The International Space Station already recycles water and manages life support in orbit, but Mars demands even more reliability and independence. A Mars crew cannot evacuate quickly if the system fails. Spare parts and repair skills are as important as the original design. Food is another challenge. Early crews will probably bring most of their food from Earth. Growing food on Mars is attractive, but difficult. Plants need light, water, nutrients, pressure, temperature control, and protection from radiation. Martian soil is not simple garden soil. It lacks Earth's living ecosystem and may contain chemical hazards such as perchlorates. Food production may begin with controlled hydroponic or aeroponic systems inside habitats or greenhouses, not open Martian fields. Greenhouses on Mars may not look like glass houses. They may be shielded, pressurized, artificially lit, and carefully sealed. Plants could help recycle carbon dioxide, produce oxygen, supplement food, and support crew psychology. But relying on crops too early would be risky. A crop failure on Earth is a problem. A crop failure on Mars could be an emergency. Water is central. Mars has water ice, but access depends on location. Ice may be buried. It may be mixed with soil. It may require drilling, heating, processing, and purification. Water is needed for drinking, hygiene, oxygen production, plant growth, cooling systems, radiation shielding, and fuel production. A Mars base will likely be built around water access as much as science. If astronauts can extract water reliably, the base becomes more sustainable. If they cannot, every leader must come from Earth. That is why robotic scouts and orbital maps matter. Before humans arrive, missions must identify where water is, how deep it lies, how pure it is, and how difficult it is to extract. Mars also offers scientific treasure. The planet once had rivers, lakes, deltas, and perhaps a thicker atmosphere. Billions of years ago, Mars may have been warmer and wetter than it is today. If life ever emerged there, signs might remain in ancient sediments, minerals, or underground environments. Human explorers could search with flexibility no rover can match. They could choose rocks, drill cores, change plans, repair instruments, travel long distances, collect samples, study ancient lake beds, explore lava tubes, inspect ice deposits, search for biosignatures. Mars science is one of NASA's strongest reasons for going. SpaceX's strongest reason is settlement and long-term survival of humanity. These motivations differ, but they can coexist. A NASA-led Mars base might begin as a research station. A SpaceX-enabled settlement might aim to grow. The early infrastructure would support both transport, power, water, habitats, propellant, mobility, communications. But the tone should remain realistic. Mars will not be easy. It will not be a backup Earth anytime soon. It has no breathable air, no oceans, no forests, no protective global magnetic field, no open agriculture, no easy rescue, no natural comfort. Terraforming Mars, making it Earth-like, is far beyond current capability and may not be practical with available resources. Even if it were possible in theory, it would take enormous timescales and planetary engineering far beyond the first missions. The real future of Mars, for a long time, is not green cities under blue skies. It is enclosed habitats under a thin pink sky. People living inside machines, stepping outside in suits, repairing equipment in cold dust, building slowly, learning painfully, surviving carefully. That is not less inspiring. It may be more inspiring because it is real. The beauty of Mars exploration is not that Mars is easy. It is that humans may learn how to live somewhere so difficult. The first base may start with only a few people. Then perhaps more cargo arrives. A second habitat, more power, a larger rover, a drilling rig, a fuel plant, a greenhouse experiment, a medical module, a workshop, a spare life support unit, a radiation shelter, an emergency return vehicle, a communications tower, then another crew, then another cargo window, Every 26 months, Earth and Mars align again. Another opportunity opens. Ships depart. Cargo lands. Infrastructure grows. If everything works, the base becomes less fragile. At first, every mission is survival. Later, operations become routine. Eventually, perhaps, the question changes. Not can we stay for one mission, but can we keep someone there continuously? Then later, can we expand? Can we manufacture parts? Can we build with local materials? Can we grow a meaningful portion of food? Can we produce fuel regularly? Can we protect crews for years? Can children ever live there safely? Can a community exist? Each step is harder than the last. But the road begins with the first systems. NASA's Moon to Mars plan is about learning those systems. SpaceX's Starship plan is about carrying enough mass to make those systems possible at scale. Both are needed in different ways. A Mars future without careful life support is fantasy. A Mars future without affordable mass transport is too small. A Mars future without science loses purpose. A Mars future without caution becomes dangerous. A Mars future without ambition never begins. The real road is somewhere between patience and boldness. NASA brings decades of human spaceflight experience. Mercury, Gemini, Apollo, Skylab, Space Shuttle, International Space Station, robotic Mars exploration, planetary science, deep space navigation, mission control, astronaut training, and safety culture. SpaceX brings rapid development, reusable rockets, manufacturing speed, and a willingness to test large systems in public, sometimes with failures along the way. The cultures are different. NASA tends to reduce risk before launch. SpaceX often learns by building, flying, failing, and improving. For Mars, both approaches have strengths and weaknesses. Human lives require caution. Large new systems require testing. Too much caution can slow progress. Too little caution can destroy trust and lives. The path to Mars will need both discipline and experimentation. It will need government and private industry. It will need international partners. It will need science and engineering. It will need money. It will need patience. It will need public support. And it will need repeated success. Not one perfect launch. Not one heroic landing. A chain of successes. Launch after launch. Landing after landing. System after system. A base is not built by one miracle. It is built by repetition. The Moon will be the training ground. Earth orbit will be the workshop. Starship may become the cargo ship. NASA's architecture may become the framework. Mars will be the test. Imagine the future sequence. First, robotic missions continue mapping Mars in detail. Orbiters scan for ice. Rovers study geology. Sample return efforts, if achieved, teach planetary protection and return operations. Meanwhile, Artemis missions return humans to lunar space and the lunar surface. Astronauts test new suits. Rovers drive near the South Pole. Power systems are deployed. Cargo landers deliver equipment. Habitats are tested. Water ice is studied. Longer stays become possible. At the same time, Starship continues development. Launch, recovery, re-entry, refueling tests, lunar landing systems, cargo flights, tanker operations. Eventually, if the system matures, Mars cargo flights, uncrewed starships or other vehicles could depart during a Mars window, carrying supplies and equipment. Some may fail, some may land far from the target, some may break. That is why redundancy matters. Do not send one cargo ship, send several. Do not rely on one power source, send backups. Do not depend on one habitat, send spares. Do not trust one communication path. Build alternatives. Mars punishes single points of failure. The first human mission may wait until cargo is confirmed on the ground. Power is active. The return plan is credible. Habitat pressure is stable. Food and water reserves are ready. Emergency systems are tested. Then, perhaps the crew launches. This will not happen casually. A Mars crew will be among the most carefully selected and trained humans ever sent into space. They will need technical skill, emotional resilience, medical knowledge, repairability, scientific training, teamwork, calm under pressure, and the ability to live in isolation for years. They will be pilots, engineers, scientists, mechanics, doctors, explorers, and caretakers of a fragile artificial world. Their spacecraft will be their first home. Mars will be their second. Earth will become a distant blue star. When they land, the first words from Mars may not be poetic at first. They may be technical, pressure stable, engine safe, crew okay, habitat link confirmed, power nominal. But later perhaps someone will step down onto the surface. A boot touches Martian dust. A human shadow falls under a pale sun. And after all the architecture, all the politics, all the testing, all the failures, all the launches, Mars will no longer be untouched by human footsteps. That moment will belong to history. But the documentary should not end there. Because reaching Mars is only the first chapter. The real plan is what happens after landing. A crew explores, a base survives, cargo arrives, fuel is made, systems are repaired, science expands. The surface becomes mapped not only by robots, but by people walking, driving, drilling, building, and observing. A Mars outpost may begin to develop routines. Morning checks, power reports, weather reports, suit inspections, rover planning, greenhouse maintenance, water extraction, science traverses, exercise, medical scans, communications with Earth, repairs, dust cleaning, sleep. The drama becomes daily life. That is when Mars becomes real. Not when the first rocket lands, but when people learn to live through ordinary days there. The future infrastructure may grow slowly. The first landing zone becomes a base camp. A base camp becomes a research station. The research station gains workshops and storage. Roads or cleared pads connect modules. Landing pads are built farther away. Solar fields spread across the ground. A nuclear reactor hums in the distance. Pressurized rovers explore beyond the horizon. Robots scout ice deposits. Fuel tanks stand near processing equipment. Habitats are covered with regolith. A greenhouse glows softly through shielded panels. A communication mast points toward orbit. Every 26 months, the sky brings another arrival season. More ships, more supplies, more people. Perhaps one day, the base has a name. Perhaps its crew watches Earth rise only as a bright dot in the night. Perhaps children on Earth grow up knowing that humans live on Mars, just as people now know that humans have lived continuously in space aboard the International Space Station. But again, this is future possibility, not certainty. Mars plans can fail, budgets can change, politics can shift, rockets can be delayed, technology can prove harder than expected, public interest can fade, accidents can happen, a single failure can reshape timelines. The honest story is not that NASA and SpaceX will definitely build a city on Mars by a certain date. The honest story is that the technical outline is becoming clearer. The road has pieces: heavy lift launch, reusable spacecraft, orbital refueling, lunar testing, surface habitats, power systems, resource extraction, cargo missions, precision landing, Mars ascent and return, human crews, long-term infrastructure. What is uncertain is when, how well, and at what scale. Mars is not guaranteed, it must be earned. The planet will not come closer because we are excited. The atmosphere will not become thicker because we are ambitious. The dust will not become gentler because a rocket is reusable. Every part must work. That is why this topic is so fascinating. It is not just a dream. It is a puzzle, a giant engineering puzzle spread across 2 planets, the Moon, Earth orbit, and deep space. NASA is building one side of the puzzle through Moon to Mars architecture. SpaceX is building another through Starship and reusability. Other companies, agencies, and nations may add pieces, habitats, rovers, suits, power, robotics, nuclear systems, communications, science instruments, cargo services, and life support. No single vehicle is the whole plan. Starship alone is not a Mars civilization. Artemis alone is not a Mars landing. A habitat alone is not survival. A fuel plant alone is not a return. The plan is the connections. Transportation connects Earth to orbit. Refueling connects orbit to deep space. Transit habitats connect Earth to Mars. Landers connect orbit to surface. Power connects machines to survival. Water connects resources to life. Fuel plants connect Mars to return. Habitats connect humans to another world. Communications connect Mars to Earth. Science connects exploration to meaning. And over time, infrastructure connects one mission to the next. That is the road to Mars, not a road made of asphalt, a road made of capability. As you rest, imagine Earth below. Blue, bright, alive. Clouds swirl, cities glow at night, oceans reflect sunlight. From Earth, rockets rise. Some carry crew, some carry cargo, some carry fuel. They meet in orbit. The spacecraft fills its tanks. The Moon hangs nearby, no longer only a destination, but a training ground. Astronauts work near the lunar South Pole. Rovers cross gray dust. Power systems survive the long lunar night. Habitats are tested. Lessons are learned. Then, farther out, Mars waits, red, cold, silent. Cargo ships descend. Dust rises under landing engines. Solar arrays unfold. A nuclear power unit starts. Robots wake. Antennas turn toward Earth. Water extraction begins. Oxygen is made. Methane is stored. Habitats pressurize. The base is still empty, waiting. Then one day a crew arrives. The first humans on Mars do not arrive alone. They arrive into a system built before them. A fragile system, but a system. A place where air has been prepared, power is flowing, water may be available, fuel may be waiting. Machines are already working. That is how survival begins. Not with bravery alone, with preparation. Mars will require courage, but courage is not enough. It needs engineering, redundancy, logistics, patience, testing, humility, and the ability to admit what is not ready yet. The most dangerous Mars plan would be one that pretends Mars is easy. The strongest Mars plan is one that respects the planet. Mars is not evil, it is simply indifferent. It has no breathable air because it never promised us air. It is cold because it is far from the sun and thinly wrapped. It is dusty because its surface has been ground by time. It is radioactive compared with Earth because it lacks our protection. It is difficult because it is another world, and that is why reaching it would matter. To live on Mars, even briefly, humans must become better at closed systems, recycling, energy management, robotics, medicine, materials, and long-term planning. Technologies developed for Mars may help Earth too, especially in water recycling, efficient energy systems, remote medicine, autonomous operations, and sustainable habitats. The road to Mars is not an escape from Earth. It should not be. Earth is home. Mars is not a replacement. Earth has oceans, forests, air, rain, soil, and a biosphere that took billions of years to form. Mars has none of that for us. Anyone who thinks Mars is easier to fix than Earth has misunderstood both planets. Mars exploration should deepen our respect for Earth. A Mars habitat shows how precious an atmosphere is. A water recycling system shows how precious oceans are. A radiation shelter shows how precious Earth's magnetic field and air are. A greenhouse under artificial light shows how precious sunlight, soil, and rain are. Going to Mars should not make Earth seem disposable. It should make Earth seem miraculous. NASA's science goals reflect this. Mars can tell us about planetary history. Why did Earth remain habitable while Mars became cold and dry? Did Mars ever have life? How do planets lose atmospheres? How does water disappear? How do climates change over billions of years? Mars is a warning and a laboratory. SpaceX's settlement goals reflect another idea. Humanity should not remain forever on one planet. A self-sustaining civilization beyond Earth could protect life from certain long-term risks and open a new chapter in human history. Whether that vision becomes real depends on many things not yet solved. But the ambition itself is powerful. Between NASA's careful architecture and SpaceX's bold transportation vision, the Mars story becomes one of the defining exploration questions of this century. Will humans become a species that visits Mars? Will they become a species that lives there? Will Mars remain a scientific outpost? Will it become a settlement? Will it teach us that other worlds are too hard? Or will it teach us that difficulty is not the same as impossibility? The answer is not written yet. It is being designed, tested, delayed, revised, launched. Sometimes exploded, launched again. That is how spaceflight often moves, not in a clean straight line, but in steps, failures, corrections, and breakthroughs. The road to Mars may take longer than people hope. It may cost more. It may look different from today's animations. It may involve vehicles not yet built. It may require international partnerships not yet formed. It may depend on technology still in laboratories. But the direction is becoming visible. Earth orbit as the staging ground, the Moon as the training ground, Starship or other heavy reusable systems as cargo carriers, resource utilization as the key to return, habitats as survival machines, power as the first infrastructure, water as the most precious local resource, Mars as the test of whether humans can live beyond Earth for the long term. As the night deepens, imagine the red planet turning slowly. No oceans, no forests, no cities, only plains, craters, volcanoes, dust, ice, and ancient stone. Above it, small moons drift. Phobos, Deimos. The sun shines smaller than it does from Earth. The sky glows pale butterscotch through fine dust. A rover track crosses the ground. A habitat light glows in the dusk. An antenna points home. A crew inside speaks with Earth, knowing every reply will take minutes to arrive. Outside, machines produce oxygen. Somewhere nearby, tanks slowly fill with propellant made from Martian air and water. A rover waits for tomorrow's traverse. A greenhouse experiment glows softly. The first base is small, fragile, temporary perhaps, but it is there. That is the dream. Not a fantasy city overnight, not a second Earth, not an easy escape. A first foothold, a careful beginning. A place where humanity learns whether it can carry life across the dark and keep it alive on another world. NASA's plan gives the journey structure. SpaceX's plan gives it scale. Mars gives it meaning, and Earth gives it purpose. Because every journey to Mars begins here, on the blue planet. Under the thick atmosphere we can breathe without machines, beside oceans we did not have to manufacture. Under a magnetic field we did not have to design, held by a world that already supports us. Maybe that is the quiet lesson of Mars. To reach another planet we must become very good at understanding what a planet gives. Air, water, pressure, warmth, protection, soil, cycles. Balance. Mars has some ingredients, but not the whole gift. Humans must bring the missing pieces, and if they do, one day the road to Mars may no longer be only a plan. It may become a route. then a supply line, then a presence, then a chapter of civilization. For now, the work continues. Rockets are tested, architectures are updated, lunar missions are planned, Starship evolves, habitats are studied, power systems are designed, rovers are developed, scientists map ice, engineers study landing, astronauts train, Mars waits. And above us, on clear nights, the red planet shines quietly. A small point of light, not close, not easy, not promised, but real, a world with a past, a world with resources, a world with dangers, a world that may one day hear human footsteps. And perhaps someday, when someone stands on Mars and looks back toward Earth, they will see our home as a tiny star in the sky. They will know that every machine around them, every breath in their habitat, every drop of water, every watt of power, every safe return path came from generations of planning and work. They will know Mars was not reached by one rocket alone. It was reached by a road built step by step, from Earth to orbit, to the Moon, to deep space, to Mars. And beyond the habitat wall, the red desert will remain silent, cold, ancient, beautiful, waiting for the next sunrise.